Okay, so I work for the Advanced Manufacturing Research Centre. We're a research body. We are part of the University of Sheffield. The reason that Boeing's there is that we do quite a lot of work with Boeing. So Boeing are our major partner, and we do generally research applications with Boeing. So I'd like to start my talk with a personal anecdote. So a couple of years ago, my wife and I moved into our first home. And like many first-time homeowners, we bought quite a lot of furniture from a well-known Swedish furniture supplier. So I went to work one day and left my wife Amanda building furniture at home. She had a set of drawers, or rather a lot of set of drawers to build. And when I got home, I found this, which is quite interesting. So yes, the door handle is not supposed to be on the inside of the drawer. So this is quite an interesting thing to find because it's obvious that this is wrong. It's obvious that this is assembly process, somewhere something has gone wrong. And it started to make me think about the work instructions. So somewhere in this mental juggling exercise of understanding how the 2D on the paper relates to the 3D in reality, the three-dimensional object, a ball was dropped in that juggling exercise and the door handle ended up on the inside of the drawer rather than the outside. It's quite obvious to see on a set of drawers that this is wrong, but what if the assembly sequence isn't quite as obvious as this? The example we had this morning was a wire harness. That isn't obvious. There is no tacit knowledge you can have about a wire harness, and therefore there is no inference you can make about the assembly sequence. So at the AMRC, we have access to rather a lot of devices. We work with pretty much every wearable technology and tablet-based devices. We are very much hardware agnostic, and our customers rather, are very interested in the maturity of these different devices. So obviously they occupy a range of maturity levels, but just how mature are they in reference to the manufacturing environment, specifically for assembly applications? So how could we quantify the maturity of AR for manufacturing? So we took two simple metrics for that. One is cost and one is quality. And derived from that, for a testing purpose in a lab, we could take cost to mean an assembly completion rate, the rate at which I can complete an assembly, and quality as the number of mistakes I might make within an assembly sequence. So roughly every 12 months or so, we take our apprentices at the training centre at AMRC and we test them with a certain number of assembly operations, giving them various different digital work instructions to assess the difference between those work instructions. So in late 2015, we tested them to build this rather scary-looking complex assembly. So it's a turbine fan blade assembly. There are some fans on top, but you can't see, or there is a fan on top rather, but you can't see it. The assembly purpose serves no mechanical functionality other than to be a complex assembly. So it's made up of different shafts and gears and bolts. So one of the nuances about this particular assembly task is you can't build it linearly. So you couldn't just build it from plate to plate, from bottom to top. So you have to build it actually in three distinct sub-assemblies that can then be brought together at the end. So it warrants the need for a set of work instructions to give guidance on how to build this. So we thought it would be the perfect test bed to test the difference between various different work instructions. So the first work instruction we tested was our control method. This is just a set of paper instructions, very similar to what you'd see on the shop floor in plenty of manufacturing environments. The next was a tablet-based AR application that just showed the assembly sequence in steps. The third one was a monocular device, a Google Glass, that showed each step of the assembly sequence as we worked through. We can also scan QR codes on the plate for in-process verification. And the last one was a interactive desktop known as a Z-Space. So it's a virtual reality device. This allows the user to manipulate the various components on screen so they can move bolts out of the way, move plates out of the way as they work through the assembly sequence. So we took two metrics from these guys as they built their complex assembly. That was the time it took them to complete the assembly operation and the number of mistakes they made during the assembly sequence. So an example of a mistake might be me putting a bolt through a plate and then tightening the nut up without putting a washer on, so that we would count that as a mistake. So let's just have a look at the results. So first of all, the time taken. So I've decided to present this as a normal distribution. So this essentially tells us if we were to choose any apprentice at random and test them using the paper-based control method, the likelihood of them finishing in about 35 minutes is quite high. Okay? So that's the paper control method. If we now overlay the results for augmented reality, we can see they're very similar. We've got a bit more certainty in the time taken, but actually there's no significant difference between the tablet-based AR app in terms of rate of completion and the paper-based work instruction. If we have a look now at the Z space, we start to see something quite interesting, and that is we can definitely say that the majority of students would finish this task in 40 to 41 minutes. So actually, what we found was the standard deviation of the task was about 5 minutes. So I could give you this task, give you the Z space, and say you will finish in 39 minutes within 5 minutes, which is quite interesting. Or at least I thought so, statistics. So when we look at the Google Glass, we're posting much slower times now. So on average, a student would finish in 46 minutes. So if we have a look at the number of mistakes made during the task, on paper, a student would very likely commit 5 mistakes. When we compare that to augmented reality, we can see now more definitely we could determine that a student would commit about 6 tasks. But quite interestingly, when we look at the difference between paper and AR, we could say that it is more likely if you had a paper-based work instruction that you would commit more than 10 mistakes. So that this is quite spread out. So it's quite difficult to assume how many mistakes a participant would take in this task. When we look at the Z space now, we're definitely posting fewer mistakes, so on average about 2 mistakes per task. Significantly fewer than in AR and paper. When we overlay the glass now, we can see again significantly fewer than AR and paper, but not quite as strongly proportioned as the Z space. So within this particular task, we concluded a few major things. So for one, the task was definitely too complex and favored students with a mechanical background. So we had electrical students and we had mechanical students performing this task, and the example I gave earlier was if we put a bolt through a plate and forget to put a washer on, that's a mistake. The mechanical students are very used to using bolts and washers and performing these kinds of operations, so they were making very few mistakes when compared to electrical students. The task was definitely too long. It took it out of the students and it definitely took it out on us. So we spent a lot of time testing the same assembly sequence over and over again. And I think the major failing of this particular task was that it was not repeatable. So once a student had completed this assembly sequence, we couldn't test them on another assembly sequence using another work instruction because they could potentially learn the assembly process. So we took that learning and we went back to the training center earlier this year, and this time we asked them to play with Lego. So we got them to build 4 randomized Lego houses. So this is the learning we took from the first test was we could take Lego, we can eliminate any kind of mechanical tacit knowledge that the students might have about performing the task because hopefully 90% of them have used Lego before. And we can also randomize the approach, so we can change the colors of the bricks, so we can create 4 very different houses, Lego houses, without the students being able to learn the process each time. So that meant we could test them on each individual work instruction. So in this particular test, I forgot to mention as well, we gave the students 4 minutes to complete the task. It's impossible to build this house in 4 minutes, so we literally just counted the number of bricks that were placed within a 4-minute period. That allowed us to keep the task short and test more and more students. So the first example was the control method. This is a set of work instructions very similar to the ones that you would find inside a packet of Lego, where we just show 6 steps in sequence. The next was a head-mounted AR device, the HoloLens, where we show the next stage of the assembly sequence on the actual assembly itself. The third one was an optical projection system where we could project the position of the brick on the assembly and also the type of brick that we need you to collect. And the last one was a monocular device again, which just simply showed the configuration of the assembly after each step. So these 2 are voice controlled as well. So in this example, the apprentice, the test subject, simply says next brick, and that's the same as on the HoloLens example. So I've just got a video of what the HoloLens example looks like. So we can see the complete house, You gesture to start building a house, and we show you exactly where the first brick is supposed to be placed. Then the participant says next brick, and then the next brick appears. Pretty simple, straightforward. So let's have a look at the number of bricks that were being placed with the various work instructions. So on the control method, the monitor, we saw you were very likely, if you were using this, the monitor work instructions, to complete 46 bricks. When we look at augmented reality, unfortunately, we can see there's a fewer number of bricks being placed on average. The monocular device, even fewer still. However, the projection system, the optical projection system, we saw a significant increase in the number of bricks that were being placed by the students in a 4-minute time period. When we look at the number of mistakes, we found something quite interesting, actually, and that is that only 22 people out of 191 even made a mistake at all. So I was starting to consider maybe the apprentices spend a lot more time playing with Lego than they do actually learning about their subjects. So when we look at the number of mistakes, the monitor device we posted, we found only 3 students out of 191 made any mistakes at all. HoloLens AR, we can see 10 students made mistakes while using the HoloLens. The monocular device, only 2. And the optical projection, we had 7. So we found that while students were using the HoloLens, and particularly the monocular device, that it was a very unfamiliar device for them to use. It took a certain amount of familiarity in getting used to how to wear the HoloLens in order to be able to leverage its full field of view. So I know, because I use the HoloLens every single day, exactly how to position it on my head to get exactly the full field of view that I need to do my task. Someone putting it on for the very first time might not necessarily know that, and we did experience that people could only see half of the assembly process. So the conclusions coming from this particular test was that we thought that it probably wasn't complex enough to see a performance improvement of AR, so placing brick after brick is probably not a complex enough task in order to see an improvement from augmented reality. And it's quite interesting, it poses quite an interesting question. Do we need to have a task of significant complexity before we start to see an improvement from using augmented reality? And our further work will start to try to quantify task complexity for augmented reality to make a significant difference. So optical projection is definitely well suited to building Lego, not playing with Lego. However, so if you ever decided to buy your children a Lego set, definitely buy them an optical projector as well, because they'll be boss at building houses. It's also possible that people definitely need to become accustomed to head-mounted AR displays before its full potential is realized. So we could start to look at learning rates while using devices over several different assembly steps and see if we're starting to see an increase in performance when compared to someone that's maybe doing it for the very first time. So that concludes the tests that we did at AMRC. Has anybody got any questions?